welcome everyone, and thanks for joining us this afternoon for our open meeting. And as usual, we have two great talks coming up this afternoon for you to listen to. So as people are just continuing to join, I will go through our familiar online housekeeping. So as you all know, this meeting is taking place via a webinar. And if you look at the top left of your screen, you should see the small green shield, which means that you're using the most up-to-date version of Zoom, which is secure. And I do also need to advise you that this meeting is being recorded. Questions can be asked at the end of each of our presentations today, but as you will be muted, please could you use the Q&A facility, ideally, rather than the chat, which is found at the bottom of your screen. And your questions will go to the panelists only. The questions today will be read out by a member of the RES editorial team, Dr. Sean Hodges. So thanks, Sean, for helping with us with that today. So before we have our talks this afternoon, I would just like to make a couple of announcements. So first of all, I'd like to announce the winners of the RES Gcse poster competition, which has been sponsored by Winton. So first of all, I'd like to announce the third prize winner, and a £25 book token is being awarded to Alexandra Campon and Alexander Pang for their poster on Kepler's laws of planetary motion, and they are from the Westminster School. And I think we should be able to just see their poster now, a fantastic poster, including both history and of course details of Kepler's laws of planetary motion, which is a fantastic poster. The second prize today, a £50 book token, is awarded to Bianca Phoenix Anti-Furco, and their poster is on the life cycle of a star and stellar evolution. And Bianca is from Greycoat Hospital School, so congratulations to Bianca. And here is the fantastic poster on the life cycle of a star. And I'd just like to highlight that all of these wonderful, cheerful diagrams are actually drawn by the person who created the poster, which is really lovely. Okay, so the first prize poster then, a £100 book token, is being awarded to George Plaistow. And George's poster is asking the question, does the aurora differ from year to year? And George comes from Marlborough College. So many congratulations to you, George. And here is George's poster. You can see a very professional looking poster all about the aurora with lots of detail. And I've had a good look at all of these posters and really fantastic discussion about the aurora, how it works, the dependence on the solar cycle, and explaining the different colours that we see in the aurora. So that's fantastic. Thanks very much for those slides. The second announcement I would just like to make is to call for applications for the Caroline Herschel Prize Lectureship, and that is now open. And the deadline is the 30th of April. And you'll find more details on that on the William Herschel Society website. The second item on the introduction to the agenda here today is to announce that the 202nd annual general meeting of the Society will take place at 4 o'clock on Friday, the 13th of May, 2022. And this meeting will be a hybrid meeting, and more information will be announced very soon on that. So please look out for those details. The third item then on the agenda is the NAM for 2022. The National Astronomy Meeting 2022 will be taking place between the 10th and the 15th of July this year, and is organised in conjunction with Warwick University. And the RES website will be updated with more information very soon. Okay, so on to the main part of our programme then this afternoon. First of all, this afternoon, I would like to introduce our first speaker, Dr. James Owen from Imperial College London, who was the recipient of the Fowler Award for Astronomy. And Dr. James Owen is a senior lecturer and Royal Society University Research Fellow in astrophysics at Imperial College London. And he also leads the European Research Council project on planetary evaporation as a window into exoplanetary origins, which aims to model the formation and evolution of exoplanetary atmospheres. James was awarded a PhD from the University of Cambridge in 2012 and has worked as a postdoctoral fellow at the Canadian Institute for Theoretical Astrophysics. He was then awarded a Hubble Fellowship at the Institute of Advanced Study in Princeton before moving to Imperial College. This afternoon, James is going to be giving a lecture on the origin of the exoplanet radius gap. Very much looking forward to your presentation, James, and I'm going to hand over to you now for you to share your screen.
Thank you very much, Emma. It's a great pleasure to be here, and thank you very much for the wonderful introduction. And yeah, I'm looking forward to giving this talk to you. So this talk is sort of going to be a mix of history, a bit of the story of the discovery and how repeated sort of advances in observation and both theory made good advances, and also sort of how the last decade in exoplanets has sort of kind of upended the picture we have of how planets form and evolve. So while exoplanetary science is quite a young subject, it's really only sort of 25, 26, 27 years old. The story that I want to talk about today really only started in the last decade, and it really began with the Kepler mission. And the Kepler mission was one of NASA's sort of leading missions to start searching for exoplanets. And it did this via the transit method. So what it did was it stared at the same patch of the sky, a small patch of the sky, looking for the dip in brightness as a exoplanet transits in front of the star. And this observation allowed us to make two specific measurements about a planet's properties. Firstly, you were able to measure the size of the planet by measuring the dip in brightness as the planet transited in front of the star. And by watching for the planet to repeatedly transit, you were able to infer the planet's orbital period. And when this mission began in 2009, 2010, we only had knowledge of a few hundred exoplanets. And what the Kepler mission was able to do was significantly transform our knowledge of planetary systems by discovering thousands and thousands more. But what was particularly amazing was it was able to find considerably smaller planets than we've been able to see previously. So this is the sort of the diagram that Kepler really gave us in terms of these two observational parameters. So the planet's radius measured from the dip in brightness, and the orbital period measured in terms of how many times we saw the planet transit. And what you can see from this diagram is most of the planets it found lay in this region here. So they rather extraordinarily had a size between that of Neptune in our solar system and that of Earth. So there is no analogous planet within our own solar system. What was perhaps even more extraordinary was that most of these planets were exceedingly close to their host star. So for reference, this is Mercury in our own planetary system. So they were much, much closer in than the terrestrial planets we have in our own solar system. And in fact, we now know that this population of planets here is by far the most common type of planetary system we know to date. So we can say now quite strongly that most stars host at least one, and in many cases they host several of these planets. And these came as a sort of a quite extraordinary surprise, right? We have no analog in our solar system. So the big question at the time was, what are these sort of intermediate type of planets? So they a scaled up version of the Earth. So or the terrestrial planets? So are they somewhat rocky in their composition, just more massive, or are they a scaled down version of the gas giants? Or perhaps they could have been something sort of quite exotic. Perhaps they were what were hypothesized to be water worlds, so planets that are predominantly made out of water. Now, one way to get at that question was the Kepler mission only provided a measurement of the planet's radius, right? So obviously these two scenarios, a scaled up version of a terrestrial planet that is rocky, or a scaled down version of a gas giant, would have quite different densities. So what was done was for several hundred of these planets, we were able to measure their masses through the radial velocity method. So the gravitational pull from the planet is able to cause the star to orbit the common barycenter of the system, and we could see the radial velocity shift of stellar lines as the star orbited back and forth, and allowed us to measure the planetary's mass. And that allowed us to make some inferences about the planetary composition. This diagram here is a slightly complicated diagram, but I'm going to walk you through it because it contains a lot of very interesting information that provided a lot of clues to what we thought was going on. So the x-axis here is a measurement of the distance the planet is from its host star, and it's given in terms of incident flux in Earth units. So an incident flux of 1 in these units would be Earth's irradiation level from the star. So the fact that most of these planets reside close to their stars is giving rise to these very, very high incident fluxes. This y-axis here is the radius of the planet scaled to the radius if it had the same composition as the Earth. So in fact, the Earth in this diagram sits at sort of 1, 1 here. And I put Mercury here for scale. It's sort of an irradiation level of a bit higher than the Earth, and it has a density slightly higher than, or it has a composition which is more enriched in heavy elements compared to the Earth. So if you were a terrestrial Earth-like planet, you would sit along this line here. So clearly, we have found many, many planets that are consistent with being terrestrial planets. If you were one of these sort of more exotic water worlds, then you would sit on this blue line here. So potentially, there could be a population of water worlds. But you see that there's a large population of planets that have radii significantly bigger than they would do if they were composed of terrestrial material or rock-iron mixtures. And these are extremely low density planets. And in fact, the only way we know how to make these planets theoretically is that they're sort of a mix of the two planetary systems. So they're a solid body or a solid core surrounded by a hydrogen helium atmosphere. So in terms of sort of what the composition is telling us about this answer of whether they're scaled up versions of terrestrial planets, certainly there are a few, or they're scaled down versions of gas giants. Well, actually, they're somewhere in between. That they're a sort of a version of a scaled down version of the gas giant with a large amount of solids in their center in a solid core. But this question couldn't answer sort of how much water ice they contained in them. Perhaps one of the other intriguing things that's going on down in this diagram is that the lowest density or largest planets, the ones with the most hydrogen helium, seem to sit at the lowest irradiation level. So as you go to very, very close to the star, higher radiation levels, in fact, these planets with hydrogen helium atmospheres completely disappear, and all we have are what we see to be terrestrial rocky-like planets. So the suggestion of the cause of this trend of smaller hydrogen helium atmospheres at higher radiation level is something we call planet evaporation. So these planets are so close to their central stars that the irradiation, particularly the X-ray and EUV irradiation that absorbed at high levels in the upper atmospheres of these planets, can heat up their atmospheres to very high temperatures, sometimes beyond 10,000 Kelvin. And this causes the atmospheres, the upper atmospheres of these planets to become thermally unbound from the planet's gravitational potential well and actually escape in a hydrodynamic outflows. These are sort of wonderful simulations I'm showing of this process where we're looking sort of top down on a planetary system here, and we're looking side on a planet here. And you can see that the radiation field in these simulations is driving this outflow away from the planet. And this causes these planets to lose mass over time. So it's not just that these planets are they're formed, and then how we see them after billions of years of evolution is exactly how they form. They're actually sculpted through this process of mass loss that causes their atmospheres to evolve and shrink over time. And early on in the Kepler mission, there was perhaps a direct example of the consequences of this process appearing. There was this wonderful planetary system, Kepler 36. And Kepler 36 contains two planets, and they're at almost the same distance from the central star. So they're very similar orbits. But they have quite distinct radii. So one planet was about 1.5 Earth radii, the other planet was about 3.7 Earth radii. And the more massive planet was consistent with having one of these sort of solid cores surrounded by a large hydrogen helium atmosphere, so a hydrogen helium atmosphere that was about sort of 10% by mass, whereas the lower mass, smaller planet was basically consistent with just being a scaled up version of a terrestrial planet. I mean, it's extremely difficult from a planet formation perspective to construct a scenario where you could form sort of two planets with very different compositions, but basically at the same locations. So the suggestion was that because this planet B here was less massive than planet C here, about half the mass, both planets, in fact, formed with a large amount of hydrogen helium in their atmospheres, and the fact that this closer in planet, planet B, was less massive, had a weaker gravitational potential, well, it was not able to resist this mass loss process and completely lost its atmosphere, whereas the more massive planet C was able to retain its atmosphere. And this is indeed what the evolutionary models seem to suggest. So these are evolutionary trajectories of the amount of mass in the planet's atmosphere as a function of time for the two planets. So the less massive inner planet is able to completely lose its atmosphere, while the outer planet, planet C, is able to retain its atmosphere. So this was a very nice example of perhaps that this is what's going on in the exoplanet population. But the real power in the exoplanet field has not been precise measurements of individual systems, but the fact that we have thousands and thousands of planets to look at. So what we began to do was study a population of planets that all formed with these hydrogen helium atmospheres and see how they evolved under this mass loss and evaporative process. So what you can do is you can take a population of planets, you can give them different amounts of material, different starting amounts in their core and different starting amounts in their atmosphere, and then you can evolve them forward through time under this mass loss process. And what we find, and it's very simple to understand, is planets close to their central stars completely lose their atmospheres, or planets with small solid cores and therefore weak gravitational fields completely lose their atmospheres. But planets that are further away from their central star, so more weakly irradiated and have more massive cores, are able to retain their atmospheres for billions and billions of years. And when you look at this process in an ensemble and statistical sense, we found that there was this dichotomy in evolution. You either ended up with planets that completely lost their atmospheres, planets that we called stripped cores, or planets that retained about 1% of their mass in a hydrogen helium atmosphere. So this is looking at it more in these observational diagnostics of a planet population here, of planet radius versus distance from the host star. And what we found was that you have this population of stripped cores and population of planets that have retained about 1% of their mass in their hydrogen helium atmosphere, separated by this distinct clean region here, which got sort of theoretically suggested or named as the evaporation valley. So the evaporation valley sort of separated planets that completely lost their atmospheres from planets that were able to retain about 1% of the mass in their atmospheres. And obviously, when this prediction was made, it was sort of nice to go and see if it was possible to pull this out of the observational data, right? This prediction that works so well for an individual system like Kepler 36, did it work for the population as a whole? Now, the problem with the Kepler data at the time was that while Kepler had found thousands and thousands of planets, the planet radius was not well known. So this was sort of in the middle of the last decade. This was roughly the error bar on an individual planet's radius measurement. Now, this was not actually a precision problem with the Kepler mission itself. It was actually a precision problem with the measurement of the star's radius. So if you remember what a transit measurement is, the way you measure a planet's radius is you measure the dip in brightness from the star. So this dip in brightness was incredibly precisely measured by the Kepler mission, but what was not known precisely was actually the radius of the star. So if you don't know the radius of the star very precisely, then you can't compute the radius of your planet very precisely. So this led to a follow-up program, the California Kepler survey, which used the Keck telescope to do high-resolution spectroscopy of thousands of exoplanet host stars to measure their stellar parameters and hence their stellar radius much more precisely, to allow us to measure the planet's radius much more precisely and shrink this error bar. And when this happened, this sort of blodge of a population revealed this bimodal structure here. So there was a population of planets with small planetary radii, about 1.3 Earth radii, and then a population at slightly larger distances from their host star that were a little bit bigger, about 2.6 planetary radii. And it's a lot more obvious if I plot this histogram here, where you have these two distinct peaks here, one at 1.3 Earth radii and one at 2.6 Earth radii. So it's very, very nice to see that this sort of this scenario predicted by this mass loss model was actually being unveiled in the exoplanet population. So as a little aside, it might seem a bit strange that this mass loss process, which is sort of almost a continuum process, should give you two quite distinct outcomes. And the explanation for this can be understood quite simply in terms of a mass loss timescale. So this timescale here on the y-axis here is the time it would take to lose your atmosphere through this mass loss process. And what I'm going to do is I'm going to take a planet with a fixed core mass, so a fixed amount of solids, and I'm going to progressively add more and more atmosphere to that planet. And as I progressively add more and more atmosphere to that planet, I'm going to change the mass loss timescale. And planetary mass loss depends on two or three fundamental things. Basically, the depth of the gravitational potential well. So how deep a gravitational potential well I have to escape from, how much high energy flux is impinging on the planet, which I'm going to hold fixed in this case by holding my planet core mass and planet distance from the star the same, but also how much of that flux I can absorb, right? How big a planet am I? So if I take a solid core and I add a very small amount of atmosphere, then the size of that planet is completely dominated by the size of the planet's core itself. As I progressively add more and more material, I'm going to eventually switch from being dominated by the core's radius to dominated by the atmosphere's radius. And as I keep going, I'm going to get a planet that's completely dominated by the atmosphere's radius. So as I progressively go from left to right here, as I'm increasing my amount of atmosphere from a core-dominated planet, I'm not really changing the radius of my planet by a great deal. So I'm not changing the amount of flux, star flux from the host star I can absorb. So I'm not changing how much mass loss I can actively do, but I've got much more mass to lose from my atmosphere. So this is going to increase my mass loss timescale. On this side, it turns out the planets expand so rapidly that they become so enormous that they absorb huge amounts of flux, and this mass loss timescale comes back down again. So it ends up looking like this. And this peaks at a radius of an atmosphere that doubles the core's radius. Because this is where I transition from being dominated by the radius of my core to dominated by the radius of my atmosphere. So now let's say I have some time in which I can lose my planet's atmosphere. This is the lifetime of my system. So any planets that start off down here have sufficient time to lose their atmosphere, and they're just going to get run away straight. Any planet that starts off here can actually lose its atmosphere, but it evolves towards safety. It gets to a point where it's even harder to lose its atmosphere. So what this process does is, while you lose mass in a continuum, it either piles planets up here, where they have a radius that roughly doubles the core's radius, and this is about a 1% hydrogen helium by mass atmosphere, or they completely strip the atmosphere. So if we look at these in a population sense, you see planets that start off large with their atmospheres, and you progressively populate this region down here where they've completely lost their atmosphere. And it was quite nice to see that this sort of model prediction looked very suggestively similar to the observational data. Now, what we can do is we can go a bit further, and we can say, now we've seen this in the observations, right, and we have a model for what's going on. Can we use that model to say anything about the underlying planetary systems, right? Because still all we're measuring is planet size and orbital period. But as this mass loss process is fundamentally set by the amount of mass in the planet's core, by fitting this mass loss model to this observed exoplanet population, we were able to sort of extract what we thought the mass distribution of the underlying planets were, so without doing any measurements. So this is some work done by a PhD student, James Rogers, at Imperial College. So you can see that we get this sort of very nice, wonderful fit to the exoplanet data. We fit the histogram in a very nice way. And this connects to why this discoveries were quite surprising. We had this sort of theoretical prior that all planetary systems might end up looking like the solar system. And in the solar system, we have this dichotomy between the terrestrial planets and the gas giants. And this dichotomy occurs roughly where we expected water ice in the planet-forming environment to condense. And if you look at early models of the planetary system formation outside the orbit of Mars, but interior to the orbit of Jupiter, the amount of solid material jumps remarkably to the fact that ices can condense. So there was an expectation to have lots of hydrogen helium in your atmosphere. You needed to have lots of ice. So what we actually found is that the majority of the solid material in these planets is actually very ice poor, in fact, very ice rich. So in fact, they're not like our typical gas giants having ice-rich cores. In fact, they're actually more like our terrestrial planets that have a large amount of hydrogen helium on their atmosphere. The final thing we were able to see was that while we know from our solar systems that the sort of terrestrial planets didn't accrete very much hydrogen helium when they formed, a very small fraction. In fact, while we see a small fraction of planets that form like our terrestrial planets in the solar system, most of the terrestrial planets we've discovered in the exoplanet population actually formed with a large amount of hydrogen helium, but were turned into terrestrial planets by this evaporation process. So I'm just about out of time, so it's been wonderful to talk to you about this, and I'll leave you with some conclusions that close-in planets are very common, and many contain these sort of large voluminous hydrogen-helium atmospheres. This mass loss process due to evaporation is extremely important from their evolution. It leads to this observed radius gap. And if you take this radius gap and evaporation model, you can actually find clues to their formation, and it actually sort of points in a very different direction to how we think the planets in our solar system form. So how these exoplanets actually formed is a bit of a mystery, and it's ongoing. So I'll stop there and I'll take your questions. Thank you very much.
Thank you so much, James, for that really fascinating talk, and very interesting to hear all about your work and the latest on those planets. It's absolutely fascinating. So I'm going to hand over to Sean, and I can see at least one question that's come in, which is exactly the question that I was going to ask, but I'm going to hand over to Sean to facilitate the questions. Thanks, Sean.
Hi, I have two questions. The first from Roger. The description of exoplanets is all very interesting, even exciting, but how does one explain its importance to a skeptic?
It's a difficult question to answer, which is sort of, it depends on what skeptical point of view you're taking on this. So I would say my take on this is I'm extremely interested in the formation and evolution of planets in general, right? So that includes Earth, right? And understanding how Earth has evolved is an extremely important problem. It even matters to us today, right? And the fact is that you can't do experiments, right? We can't take another Earth and change things. We can't say, right, change our geology and see how Earth may have evolved in a different way. But you can do that through exoplanets, right? They provide a statistical ensemble for how planetary systems evolve. So it's extremely important to understand exoplanet evolution because it provides an understanding for geophysical evolution. So by understanding how exoplanets evolve, we can hopefully gain a better insight into how the Earth evolved.
Okay, the next question is, what impact does the magnetic field of the planet core have on the loss of the atmosphere? The magnetic field of the Earth appears to be responsible for retaining the atmosphere, and Mars appears to have been stripped after the magnetic field decayed.
Yeah, so that's a fantastic question, and the analogy you have of Earth and Mars plays exactly the same analogy we would have for these exoplanets. So if these planets had a strong magnetic field that did not decay away, this would have suppressed this mass loss process. So the interesting thing is that we can only fit this model to the data successfully if the magnetic fields are weak and did not play a strong role in retaining the atmosphere. And by weak, I mean roughly that the planets have a sort of a magnetic field that is weaker than about 1 Gauss at their surface.
Okay, we've got time for one quick one. I apologize to everyone who didn't get theirs answered. How exceptional is the solar system and how come?
The first question is a little bit easier to answer. So from the perspective of having a giant planet system, we know that giant planets with giant planet-like orbits, so Jupiter-like orbits, are about a 10% occurrence. We also know that not having one of these super Earth or sub-Neptune style planets is around a sort of 10 to 20% occurrence. So the best outcome, the solar system is sort of a roughly 10% outcome of planetary system formation. At the worst, it's a 1% outcome. So the solar system is rare, but not crazy rare. How come? I could speculate probably for another hour, but the best answer I can give you is no one has a convincing argument at the moment.
Okay, I'll hand back to Emma.
Thank you so much, Sean, and thanks again, James, for a fantastic talk and for answering those questions. Okay, so we're going to move on to our next speaker this afternoon. I'd like to introduce Dr. Julia Stavarts from Imperial College London, who was the recipient of the Winton G Award for 2021. So Dr. Julia Stavarts is a Royal Society University Research Fellow in the Space and Atmospheric Physics Group at Imperial College London. She received her PhD from the University of Colorado in Boulder in 2016, where she held a National Science Foundation Graduate Research Fellowship. She was recently awarded the Winton Award in Geophysics from the Royal Astronomical Society and the Basu US Early Career Award for Research Excellence in Sun-Earth Systems Science from the AGU in 2018. So the title of Julia's presentation this afternoon is Turbulence-Driven Magnetic Reconnection in Collisionless Plasmas, New Insights from NASA's Magnetospheric Multiscale Mission. That was a bit of a mouthful. I'm going to hand over to you, Julia. Thank you very much.
Thank you for the very nice introduction. Just move this onto another screen. Okay. So I'm going to be talking about the role of magnetic reconnection within turbulent plasmas. And this is really work that has been enabled by the very high quality measurements from NASA's Magnetospheric Multiscale mission, which I'll tell you a bit about what that is in a little bit, right? So turbulence refers to the complex, highly nonlinear dynamics of fluid or plasma systems. It occurs in plasmas that we find throughout the universe, whether that is, plasmas within our heliosphere, like solar corona and solar wind, or the plasmas that we find in the magnetospheres of the Earth and other planets. But it's also found in astrophysical environments like the interstellar medium or accretion disks, like you find around black holes, or even in the kind of the intracluster medium in galaxy clusters. And within plasmas, turbulence generates fluctuations across kind of a wide range of scales, and it's responsible for transporting energy between different length scale fluctuations, which helps to facilitate the dissipation of kind of large scale fluctuation energy within the plasma. So you can see kind of example of what a turbulent environment might look like in these simulations that I worked on with one of my collaborators, Luca Franchi. So you can see these panels are showing the magnitude of the magnetic field within a turbulent simulation, as well as the magnitude of the current in a turbulent simulation. And you can see that there's lots of different complex structures in both the magnetic field and the current within these systems, and across lots of different length scales. You have these larger blobs and smaller scale fluctuations in between them, right? And so within astrophysical plasmas, these turbulent fluctuations can play a role in forming the structure that we see within the universe. It can also play a role in mixing together different plasmas from different environments. And the dissipation of these fluctuations can play an important role in the heating and acceleration of particles within the plasma. And so in a broad sense, the kind of questions that I and others that study turbulence are interested in are how the nonlinear dynamics within behave within a turbulent plasma. So even though turbulence is found in hydrodynamic systems, because of the interaction with the magnetic field, as well as the fact that in many space and astrophysical systems, there's a relative absence of collisions, they're nearly collisionless. There's lots of different nonlinear as well as linear terms in the kind of dynamical equations, and how those different terms interplay with each other can lead to very different behaviors of the turbulence. And so there's an open question of how turbulence actually behaves in different kind of plasma environments. And it may not be the same in every different plasma environment. Also interested in how energy is ultimately dissipated within turbulent plasmas. So like I said, many space plasmas are nearly collisionless, and so you no longer have collisional resistivity or viscosity being responsible for dissipating the energy in the turbulent fluctuations, and it has to occur through kind of the kinetic interactions between the electromagnetic fields and the particles. So understanding how that process actually occurs is still very much an open question. And then how does the turbulence within these kind of space plasma systems impact the kind of overall environment? Right. So one of the kind of processes that for a long time has been thought to be important within turbulent environments is magnetic reconnection. So magnetic reconnection is a process where you envision you have oppositely directed magnetic fields that may be caused by having a current sheet or a twisted magnetic field. And those oppositely directed magnetic fields get compressed together, and if the gradient is in the magnetic field is small enough, then the particles that are gyrating around the field lines can decouple from the magnetic field. And once that happens, you're able to cancel out the kind of oppositely directed component of the magnetic field, which changes the magnetic topology and releases the energy that you've kind of stored up in this compressed or twisted magnetic field. And that energy is then converted into kind of bulk plasma flows, so you can accelerate jets of plasma out either side of this kind of reconnection point. Or you can also convert some of that energy into kind of non-thermal particle acceleration, for example, or heating of the plasma. And you can also generate lots of plasma waves, right? And so in the context of a turbulent plasma, there are a few different ways that, reconnection and turbulence can relate to each other. So you can have kind of large scale current sheets that undergo reconnection, and then that reconnection can act as a driver for turbulence within the plasma. That is, the reconnection jets that are formed can destabilize, generating lots of kind of fluctuations in these reconnection jets. The other way that turbulence and magnetic reconnection can relate is that turbulent fluctuations themselves can kind of twist up and tangle up the magnetic field lines. And so you form lots of small scale current sheets. And those current sheets can act as locations for magnetic reconnection. So you can both have reconnection driving turbulence, but you can also have turbulence driving small scale reconnection events. And so it's this kind of turbulence driven magnetic reconnection scenario where you've got these little reconnection events occurring at the interfaces of these kind of twisted magnetic field structures that are formed by the turbulence that I'm going to be talking about today, right? And so relatively recently, motivated by some observations from the magnetospheric multiscale mission, there's been some work looking at how reconnection in a turbulent environment actually behaves within a collisionless plasma. So in a collisionless plasma, at some point you get to length scales comparable to the kind of motion of the individual particles in the plasma, so the gyro motions or the inertial lengths of the ions or electrons. And so you start breaking down your kind of fluid approximation of how the plasma behaves. And it turns out that if the kind of length of your current sheets that are reconnecting in the turbulent environment is short enough compared to these kind of characteristic length scales for the ions, then you won't be able to kind of fully couple in the positively and usually heavier ions within the plasma into the newly reconnected magnetic field lines before they kind of fully relax at the kind of ends of your current sheet. Right, and so you won't accelerate kind of these fast plasma jets with the for the ions, but you will still form the jets and the kind of negatively charged electrons, right? And so this kind of mode of reconnection, which is kind of unusual, has been come to be called electron-only reconnection, in contrast to kind of the more traditional view of magnetic reconnection, which I'll refer to as ion-coupled reconnection, where you both accelerate electron jets out from the reconnection site, but there's enough space that eventually the ions also couple into the newly reconnected field lines and form ion jets as well. And so recent numerical simulations have kind of looked at idealized reconnection events where you kind of artificially set how long the current sheet is by setting how large your simulation domain is. And you can see this scenario where for very large simulation domains, you have kind of ion reconnection jets that are at the kind of expected speeds that you would think of. And then as you reduce the kind of size of your simulation domain, so you're limiting the length of your current sheets along the outflow direction, these ion flows become slower than you would expect from theory. And eventually the ion outflows are nearly non-existent, right? And you have this kind of electron-only mode of reconnection. And so in the context of a turbulent environment, you would imagine that if the sort of characteristic size of the twisted up magnetic fields that are formed by the turbulence, which is going to be kind of related to the scale that you're stirring up the turbulence at, is small enough, then you may get this electron-only form of magnetic reconnection as opposed to the more traditional ion-coupled reconnection. And this could potentially have an impact on, say, how you partition energy between ions and electrons, either in terms of the kind of nonlinear dynamics, as well as in terms of potentially any particle acceleration or heating that happens as a result of these magnetic reconnection events. And so in a turbulent environment, this kind of average size of the magnetic structures is what we refer to as the magnetic correlation length of the turbulence. Right. So in relatively recent years, we've had some really high quality measurements from a mission called the Magnetospheric Multiscale Mission, right, that have really allowed us to have a new view on what's going on with, observationally be able to look at what's going on with these turbulence-driven magnetic reconnection events. So Magnetospheric Multiscale is a formation of 4 identical Earth orbiting satellites. So it was launched in 2015, almost exactly 7 years ago, actually. I think it's on Sunday, it will be 7 years since the MMS launch, which is quite exciting. It makes me feel a little bit old at this point, but and the kind of unique thing about MMS is that it made exceptionally high resolution measurements, and because it was 4 spacecraft, you had multi-point measurements, and the goal of MMS was to have very closely spaced satellites. So we got down to a separation of around 5 kilometers, which sounds like a long distance, but in terms of space plasmas, that's an incredibly small distance. It's approaching the kind of characteristic length scales of the electrons within the plasma. With MMS, we make kind of measurements of the 3D magnetic fields and 3D electric fields in the plasma. We make measurements of the full particle distribution functions for the ions and electrons. And for MMS, this was particularly high resolution. So we get electron distribution functions with 30 millisecond resolution, which is something like 100 times faster than previous missions. And also because you have these multi-point measurements, you can then do things like measure gradients within the plasma. And so in particular, these very high resolution measurements of the particles in the plasma, and in particular the moments of the distribution functions, have allowed us to look at kind of these small scale reconnection events that are formed by turbulent dynamics in greater detail than we've ever been able to before. Okay. So one of the regions that MMS makes really good measurements within is the region that we call the Magneto Sheath, which is the shocked solar wind plasma that's downstream of Earth's bow shock and upstream of the kind of boundary between Earth's magnetic field and solar wind, which we call the magnetopause. here's just an example of what some Magneto Sheath data would look like as observed by MMS. So over here, you have the solar wind plasma, where you have these fast flow speeds that are going back towards Earth, and relatively weak magnetic fields. You have this sharp discontinuity here, and that's the Earth's bow shock. And then downstream of the bow shock, you have all of these intense fluctuations in the magnetic field, as well as the velocity, as well as in the current, in pretty much every parameter, right? And this is kind of turbulence that's being stirred up by the kind of shock processes and instabilities that happen within the Earth's magneto sheath. And so with MMS, we can directly measure the kind of currents within the plasma, and we see that we have these very spiky and intense currents that are formed within the plasma, and these kind of small scale current sheets can all be potential locations for magnetic reconnection. And so in the work that I've recently been doing, we've been going through and kind of systematically looking at these small scale current sheets within the Earth's magneto sheath to try to see if we can identify individual magnetic reconnection events that are occurring. And in fact, we can. So recently we've identified a range of different intervals of magneto sheath turbulence within the magneto sheath turbulence with MMS, and in particular regions where we had the highest resolution measurements from MMS. So that we pulled out kind of 60 of these intervals. They're distributed across the dayside magneto sheath. All of these points correspond to different intervals. And then we've gone through and systematically looked for these individual magnetic reconnection events. And so we did this in sort of a partially automated way. So where we went through and looked at all of the most intense current sheets within each of these intervals, and then we looked for some basic properties that we would expect within magnetic reconnection events. So we looked for kind of these fast electron outflows that we would expect to have, reversals in the magnetic field component that we would expect, which would be this kind of reconnecting magnetic field, this oppositely directed component of the magnetic field. And then we went through each of those kind of automatically selected current sheets and looked in more detail, manually in more detail for kind of the more detailed kind of structures that we would expect to see in actual reconnection events. And I'll show you what some of those look like in the next few slides. But after we did this whole process, we found 256 of these small scale magnetic reconnection events across these 60 different intervals. That corresponds to around 10% of the kind of the most intense current sheets within the magneto sheath undergoing magnetic reconnection. And so we now have this kind of large data set of database of these reconnection events that we can start to look at statistics and compare with simulations of turbulent reconnection. Right? So here are just a few different, a couple of examples of these kind of reconnection events that we pull out. So we see examples of reconnection events both with and without ion outflows. So that could be consistent with this kind of ion coupled and electron only reconnection. However, with spacecraft observations, essentially the spacecraft is more or less sitting in one location. It's slowly moving around its orbit, but the plasma dynamics are moving these current sheets over the spacecraft. And so typically what you have is you have a single trajectory cutting through an individual magnetic reconnection event. And so most of the events that you see will be that MMS is cutting across one side of the outflows. Every so often you'll see kind of different outflows with different spacecraft, or you'll cut through in a different direction and be able to see both outflows. And those provide a bit more confirmation that you're actually seeing magnetic reconnection events. But both of these events that I'm showing here are reconnection events where we're cutting across one of the outflows. And so in this first event, which appears to be an ion coupled reconnection event, you can see that there's this reversal in the what we call the BL component of the magnetic field. So that's this oppositely directed component of the magnetic field that's reconnecting. And then inside of this reversal, you have this perturbation to the electron velocity, which is an electron jet, as well as this perturbation to the ion velocity, which is an ion jet. And the key thing that you look for is to have this kind of change in the correlation between the L component of the magnetic field and the velocity, which corresponds to this kind of peak in the velocity at the center of this magnetic field reversal, right? And similarly, over on this electron-only reconnection event, you can see that we have, have this reversal in BL, as well as this perturbation in the electron flow, which is the electron jet within this BL reversal. But there's not a clear signature of an ion jet being formed. And in addition to kind of these jets and magnetic field reversal signatures that we see, we can also look for some of the more subtle signatures of magnetic reconnection. So for example, perturbations to the magnetic field in the out of plane component, which are called Hall magnetic fields, that are related to the difference in the ion and electron motions. So you can see these little bipolar variations in the magnetic field within the current sheets, and that's this kind of perturbations to the out of plane magnetic field within the magnetic reconnection event. We can also see that you have these kind of peaks in the dot product between the current and the electric field, which, if you think back to Poynting's theorem, is telling you that energy is being exchanged from the electromagnetic field back into the particles, which is exactly what we would expect to see within a magnetic reconnection event. That is, the magnetic field is doing work on the particles and accelerating them out into flows and leading to heating and acceleration. Right. So with these, so of course, because we only have these individual trajectories through a given reconnection event, that means that it's somewhat difficult to uniquely tell for an individual event whether you actually have ion-coupled reconnection going on or electron-only reconnection going on, because you could imagine if you cut through an ion-coupled reconnection event at a distance kind of closer to the reconnection point, then you might see a signature that looks sort of similar to electron-only reconnection. And that's kind of a limitation that we have in spacecraft observations, because we only have these individual trajectories through these events. And there's a couple of different ways we can try to address that. One way would be to compare the observations with numerical simulations, where you can see the full 3D configuration of the reconnection events and actually see if you ever get ions coupling into the reconnection events. And the other way is to look at the kind of overall statistics of this large database of events that we have from MMS. So recently I've been working with some collaborators at Goddard Space Flight Center, looking at directly comparing kind of the reconnection events that we see in the MMS observations with simulations of a bow shock-like magnetic shock in a particle and cell simulation. And so in these simulations, we aren't actually simulating any particular one of these reconnection events. Instead, we're simulating the shock, right? And so here's kind of the subset of the overall domain. So over here, you've got the solar wind coming in, solar wind-like plasma in the simulation coming in. It undergoes a shock, and then you generate all of these fluctuations, and this would be like the Magneto Sheath. And then this process of the undergoing a collisionless shock generates all of these fluctuations within the simulation. Those self-consistently generate magnetic reconnection events. And so Naoki Besso here has gone through and identified all of the little electron-only and ion-coupled reconnection events within this shock simulation, and we can go in and look at trajectories through these self-consistently generated shock reconnection events within the shock simulation and compare them to the reconnection events that we see in our observations. And interestingly, so this is a different reconnection event from what I saw on the last slide. In this one, we see this large bipolar signature in the electron flows. And so what we think is going on is we're traversing the current sheet at a much shallower angle. So we're cutting through both of the reconnection outflows in this simulation. And so we can compare that to a similar trajectory that was seen in one of the electron-only reconnection events in the simulation. And we see a number of similar features between the observed reconnection events and the simulated reconnection events. And in this study, we were actually particularly interested in what the reconnection rates within the simulations were. Right, and so we find that we have these intense out-of-plane electric fields within the observations as well as in the simulations that are much larger than we would expect for kind of ion-coupled reconnection. So there are much faster reconnection rates. We can also go through and look at the statistics of the reconnection events within the simulation, within the observations, and look at how they relate to the expectations for electron-only and ion-coupled reconnection. So here we're looking at the thickness of the current sheets and the speed of the ion and electron outflows. We find that we have kind of a range of different current sheet thicknesses at these reconnection events, and many of them are kind of sub-ion scale current sheets, which would be more consistent with electron-only reconnection. And for the events where we do see ion outflows, they tend to be the thicker ion scale current sheets. This is kind of consistent with there being a population of electron-only reconnection and possibly a population of ion-coupled reconnection. And we can look at if the kind of properties of the reconnection events vary with the correlation length as we would expect for this kind of, is the prevalence of electron-only reconnection more common when you have a short correlation length, so small twisted magnetic field structures in the turbulence. And in fact, we see a tendency for thinner subproton scale reconnecting current sheets when you have shorter correlation lengths, which is consistent with electron-only reconnection going on. So we can ask the question, what happens if you go to much larger correlation lengths like you would see in, say, a more astrophysical plasmas or in the solar wind? And that's kind of an open question that we're looking at. And you can imagine different scenarios that might happen. So maybe the naive one would be that you'd have ion-coupled reconnection at these very large correlation lengths. But it could also be that as you go to larger scale separations, you may get additional instabilities in the turbulence and start fragmenting the current sheets, and maybe you start to get electron-only reconnection going on at these much larger effective Reynolds numbers of the turbulence in a plasma like the solar wind with very large correlation lengths. Or you could imagine maybe turbulence becomes less common at larger correlation lengths. And so there's one of the things that we're hoping to do is to be able to look at solar wind observations and start to get a better handle of what the reconnection events in the solar wind, how those may relate to the turbulent dynamics. I'm not going to dwell on this slide in the interest of time, but the point is we've been looking at some follow-up questions about how these reconnection events influence the nonlinear dynamics, as well as how they factor into the turbulent dissipation. At least in the Magneto Sheath, it seems like they could play a non-trivial role in the dissipation of the turbulent fluctuations. So I'll leave it there, and I'm happy to answer any questions.
Julia, thank you so much for that fantastic talk. Again, a very complex topic, but you've explained your work and the field very clearly indeed. So thank you very much for that. I'm just going to hand over to Sean to see if there are any questions.
At the moment, I think you've bowled over the audience with your brilliance. I have one quick question. Is there a planned successor to MMS for improved measurement?
Well, so one of the big things that would help to go beyond MMS would be, so MMS was four spacecraft in a small scale formation. So that lets you compute three-dimensional gradients, but you can only really look at kind of one length scale at any given time. And then you're relegated to looking at trying to sort out the temporal evolution versus the spatial evolution as structures get advected over you. So to get around that, the idea would be to have a larger constellation of spacecraft. So you might go up to 9 spacecraft or something. and make measurements at multiple points all at once. And so, in fact, there was recently a mission called Helioswarm that was selected by NASA. That is, the aim is for it to launch in 2028, I believe, and that will be focused at looking at length scales, kind of in the MHD fluid scales and the solar wind in particular, but it'll also encounter the Magneto Sheath. So I'm quite looking forward to looking at that data and seeing what we can do with regards to turbulent reconnection with those new data sets.
If we have time, we have one question now from the audience, or two suddenly. Does reconnection increase during geomagnetic storms due to increased turbulence, greater amounts of plasma, or a combination of both?
So in terms of geomagnetic storms, usually you're thinking about more the kind of large scale cycle of reconnection in the magnetosphere, which we call the Gcse cycle. So you have kind of, if you get southward IMF in the solar wind that impinges on the Earth's northward magnetic field, and you get reconnection on the day side that then brings flux into the magnetotail. And you get reconnection there that can accelerate particles back towards Earth. There is a really interesting question. So in that sense, that's a little bit different than the small scale reconnection we're looking at in the turbulence. But I think there is a really interesting question of how the turbulent dynamics in, say, the Magneto Sheath or other regions impact the kind of overall dynamics of the magnetosphere. So you can imagine that the turbulence is going to perturb the kind of magnetopause, and it may lead to more patchy magnetic reconnection or lead to Kelvin-Helmholtz instabilities that may have an impact on sort of the more large-scale geo-effective magnetic reconnection that's going on in the magnetosphere. But that's an area that hasn't been looked at as extensively, and so I think there's a lot of opportunity to look at kind of the space weather impacts of plasma turbulence.
Thank you very much. I think I'll hand back to Emma for lack of time.
Thank you very much, Sean, for doing that. And thanks again, Julia, for your talk and also for answering those interesting questions. So that brings us to the closing remarks for our meeting this afternoon. And finally, I would just like to give notice that our next monthly A&G open meeting of the Society will be on Friday, the 8th of April. So I look forward to seeing many of you for that meeting.